Okay, so in this example, we're going to determine the magnitude and coordinate direction angles of the resultant force of these two forces. So we do this exactly the same way that we did in 2 dimensions. We just have this z component. And that is, we start by summing the force, or we sum the forces, yes, but we start by writing the forces in Cartesian form. So we'll start with F1, okay? And F1 is given like this. So I've got this dark blue triangle, this light blue triangle, okay? I've got a right angle right here on the dark blue triangle, and I've got a right angle right here on the light blue triangle, okay? So I can break this up. Here's my x component, here's my y component, and here's my z component. So it's going to be plus x minus y plus z. So I have plus, minus, plus. That's where that comes from, okay? Now I need to know the length of the side of this triangle, and this triangle. The z component is actually the easiest component. The hypotenuse of this triangle is 80, okay? The z component is opposite of 30, so it's going to be 80 sine 30, which is I have right here in the z component, okay? Now, again, remember that prime axis. This is the hypotenuse of the dark triangle and the adjacent leg of the light triangle. So the length of this side is actually 80 cosine 30. Okay? And you see that 80 cosine 30 shows up in both the x and the y components right here. That's the length of this side. That's actually the hypotenuse of this triangle. So when trying to figure out the y and the x-axis is adjacent to the 40 degrees. So I take this hypotenuse, 80 cosine 30, times the cosine of 40 to find the length of the x component. Likewise, the y component is opposite of 40, so it's going to be sine 40, okay? The hypotenuse is 80 cosine 30, right, times the sine of 40 because it's opposite of it. So this big long equation here is actually the F1 written in Cartesian form. And you can plug that in your calculator and actually get numbers. Now F2 is very simple. It's just acting downward in the negative z direction, so I just get minus 130k. So once I've written both vectors in Cartesian form, I simply add up the x, add up the y's, add up the j's. So adding up the x's, the 53.1 is just what I've got here because there's no x here. Okay. Adding up the j components, the 44.5 is simply this because I'm adding it to 0j into F2. Okay. And this would be 40 minus 130 gives me the minus 90 in the k direction. So my resultant force is actually given right here. It's 53.1i minus 44.5j minus 90k. And in fact, I prefer this sort of way of writing it. But the problem does ask for the magnitude and the coordinate direction angle. So moving forward, the magnitude is simply the square root of the sum of the squares. So 53.1 squared plus 44.5 squared plus 90 squared equals 114. That's the magnitude of the resultant of these two things added together. Okay. Again, I prefer this sort of writing. This gives me a better idea of what direction things are going in. But if I do want to find those coordinate direction angle, I just use those equations we talked about in the lecture. Alpha, beta, gamma is just going to be the inverse cosine of ax over a, ay over a, and az over a. So I get the 53.1, negative 44.5, negative 90. Plugging those into your calculator, I get these angles. Now the problem is these angles are really hard to visualize. Once I go beyond 90 degrees, it becomes very challenging for me to actually visualize what this direction actually is, which again leads me back to what I said, where I prefer this sort of representation of the vector. But the problem asks for the magnitude given here and the coordinate directions given here.